looking at section 234, which is titled Similar Triangle Proofs. And we're going to answer the question, how can I justify it? So for question number 9, we want to know, does angle-angle similarity always work? You can use your tracing paper if you want, but I prefer highlighters if you have them. If not, you can use pens, or you can just write pink, pink, and green, green if you want to. All right, so it says, I think it says Matt knows that if two triangles of a triangle are congruent to two angles of another triangle, then the triangles will always be similar. But now his teacher has asked him to use transformations to explain why angle-angle similarity always works. Eliana says, let's start with the diagram. I'm going to name my triangles triangle PQR and triangle TUV. I know that two pairs of angles are congruent, so I can mark angle P congruent to angle T. I did that with my greens. And angle Q congruent to angle U. I did that with the pinks. Okay? Do we know anything else? If you know anything else about the triangles, mark the information and then justify your reasoning. Okay? Because we know that pink is congruent to pink and green is congruent to green, we can also know that angle R would be congruent to angle V by the triangle Sum Theorem. Because if you subtract these two from 180 and you subtract these two from 180, that's going to leave these two angles congruent as well. Okay? Scott says, I think it will help if we can match up two of the congruent angles. Eliana says, well, if the angles are congruent, that means there are rigid transformations that will move one onto the other, right? Let's map angle P onto T. Okay, so any of the rigid transformations, the ones that keep the figures the same size, so like rotation, translation, and reflection, all keep them the same size, versus the dilation changes the size. So dilation is not considered rigid. Is Ileana correct? Justify your answer and draw a diagram that shows that triangle P prime, Q prime, R prime, and triangle TUV after the sequence of transformations. Okay? So we just say, yes, Eliana is correct because of the definition of congruent, and you can use any of these transformations to redraw your triangles. You could use a rotation, you could use a translation, or you can use a reflection. You can't use a dilation. Dilation's not going to keep it the same size. Dilation's going to make it larger or smaller. Okay? Part C. What do the angle relationships in your diagram tell you about line QR, Q prime, R prime, and line UV? Explain that angle Q prime is going to be congruent to angle V. Why? Because the lines are parallel. Okay, we're going to see that down at the bottom in the drawing. Okay? Ileana says, hey, that looks like those problems we did with rubber bands. We just dilate the triangle P prime, Q prime, R prime, and then we'll have triangle TUV. Scott says, but we don't know the side length, so how do we dilate so that the vertices match up? Help them write a scale factor that will take point Q prime to point U prime if point T is the center of the dilation. Hint, it might help to start with the numeric measures for the side lengths and then think about how to write the scale factor more generally. Okay? So you would do TU is to PQ, and look, you'd have to look back up at the original triangle. TU would match up with PQ, or on this triangle, TU would match up with P prime, Q prime. Kendall is confused. Okay, I know that parallel lines stay parallel after a dilation. So if Q prime, R prime, and line UV are parallel, and point Q prime, Q double prime coincides with point U, then point R will coincide with point B. But my diagram doesn't look like Eliana's diagram. Will it still work? See Kendall's diagram it right. Will the dilation you described in part D still work? Yes. A dilation will work. If the dilation is greater than 1, it's going to make it larger. If the dilation is less than 1, it's going to make it smaller. It's going to shrink it. Okay? Less than 1 would either be a fraction or a decimal, like 0.5, or 0.75 is going to shrink it. Okay? Anybody still writing at the bottom of page 27? Okay, awesome. Turn it over to the top of page 28. All right, on question 110, it says Janelle and Cameron were working on their homework together. For the diagram at right, Cameron wrote the equation 4 over 6 equals 5 over 5 plus x. Is his equation correct? Explain. If needed, revise his equation and then solve for x. Okay? So Cameron, and underneath this hole punch, there's a 2. Those hole punches always get in the wrong spot. There should be a 2 there. You just can't see it. It's under the hole in your paper. So Cameron did 4 to 6 and set that equal to 5 over 5 plus x. Okay? This is correct. Why? Because he did the right side, right top side of the triangle. So if like we kind of split the triangle down the middle here, he did the right to the right total. He added the 4 and the 2 to get the 6. Okay? Set that equal to the left side, which was 5, over the total, which is 5 plus x. Okay? That sets up the proportion correctly. Then to solve your proportion, you do the cross product. So you're going to multiply diagonally this way and diagonally this way. So you distribute out 4 times 5 is 20. 4 times x is 4x, and 6 times 5 is 30. Then to get the x by itself, you subtract 20 from both sides. So you have 4x equals 10. And then when you divide by 4, you get 2.5. That means this little portion down here is 2.5. After Cameron did that, then Janelle wrote the equation as 4 over 2 equals 5 over x. Janelle says, oops, I wrote the wrong equation, but I still got the same answer. How did Janelle come up with her equation? Okay. The answer is that Janelle is also correct. Okay, there's more than one correct way to set up your proportion. How did Janelle do it? Janelle did the right side top number over the right side bottom number. She set that equal to the left top number over the left bottom number. Okay? Then she plugged in the numbers. So you'd have 4 over 2 equals 5 over x. That's the proportion. Then you do the same thing. Every time to solve a proportion, you just do the cross product. So you multiply the 4 times the x and the 2 times the 5, and you get 4x equals 10. Divide both sides by 4, and you get 2.5. That's the same answer that Cameron got up here in part A. They got the same answer. They set it up slightly differently, but they're both correct. Okay. Question number, or letter C, it says, Cameron asked Janelle, will that always work? Can we prove it? So he drew the figure at right. What information should he add to his diagram? And what does he need to prove? Okay. The information that you need to add to this diagram is that DE, this segment right here, is, who knows what this little double stick symbol means? Anybody know? Means it should be parallel to BC. So here's BC. That segment and that segment are parallel to each other. Okay? So we're going to prove that A over B is equal to C over D. So we just took the left side and set it equal to the right side. Top to the bottom, top to the bottom. Okay? As long as you set your proportion up consistently, then you the same way, then you're going to have congruent proportions. Part D says, with your team, write an equation that Janelle's method will always work. Or provide a counterexample. First, use the definition of similar triangles to write a proportion comparing the corresponding side lengths. So in this diagram, you want to say that angle D is congruent to angle B. Why? Because it's sliding down this side, which could be a transversal, and it would make them corresponding angles. They also share angle A. Angle A up at the top is in both the smaller triangle and in the larger triangle. So it's congruent to itself. It's what we call a shared angle. Okay? Which makes the small triangle and the larger triangle in this diagram similar by angle. Okay? If the two triangles are similar by angle, we can set up this proportion. A over A plus B equals C over C plus D. Okay? That means for part E, we can use algebra to rewrite the proportion you wrote in part D to show that A over B equals C over D. The relationship that you proved is sometimes called the side splitter theorem. Write the relationship as a conditional statement. So we're just going to prove it algebraically. So if we have A over A plus B equals C over C plus D, we take our proportion and we do the cross product. That means we're going to have A times the other denominator, C plus D, set it equal to C times the other denominator, A plus B, and distribute. A times C is AC, A times D is AD, and then on the right side of the equal sign, we have C times A, which is also AC, and C times B, which is BC. On both sides of the equal sign, we have an AC, so we're just going to subtract it, and we're left with AD equals BC. Which is the same thing that happens if you just have A over B equals C over D. So algebraically, that's what it looks like. Any questions on part E? Anybody still writing? Good? Okay, flip over to the top of page 29. All right, question 111 says, this is the side splitter converse. So in problem 110, you prove that if a segment intersects two sides of a triangle and is parallel to the third side of the triangle, then the lengths of the parts are proportional. Now you and your team will prove the converse of the side splitter theorem. So for part A, they want you to start by writing the converse of the side splitter theorem as a conditional statement or as an arrow diagram. I wrote it as a conditional statement. I just prefer the if-then because that's the way I learned it when I was in high school. But if you like the arrow thing, you can use the arrow thing, okay? So we're going to take the then part of the statement and we're going to say if the segment intersects two sides of a triangle so that the lengths of the parts are proportional,